So, hi everybody, welcome to the afternoon session. So, our first speaker is David Fernandez Duque, who is going to talk about Noetherian Gödel logic.
Thank you. Well, it's very nice to be here. I think this workshop is a very good idea, and we should have more events like this. Now, I do feel a little bit like a wolf in sheep's clothing because I don't do that much reverse math. So I had to think a little bit about what to present. We have this very old ongoing project with Paul and Keita and Henrik Tausner, and we're supposed to finish a paper, a very nice reverse math paper that we're supposed to hand in July. But the problem is that we did the math 4 years ago and we gave so many talks about it, so we didn't want to do that again. And then there's a project on Goodstein principles with Andreas, which I started to think more and more that it could be classified as reverse math if you think about it in a certain way, but it's not really traditionally considered reverse math because you're not proving equivalences to theories. So I landed on something that I thought people would enjoy, even though it's not. I really don't think it could be classified as reverse math at all. But it has things with, so the flavor of the proofs and the results is very reverse math. And I think there are some nice motivations for everybody in the room. Now, I'm definitely not a philosopher. I have no background in philosophy. So I hope I don't say anything too dumb in this slide. But this is a talk about a certain fuzzy logic, Gödel logic. And what we do here is what is a sort of non-classical reasoning, and it's motivated by vague predicates. So you have this very well-known paradox that if you have a grain of sand, you remove one grain. A heap of sand, and you remove one grain. So have a heap. You remove one grain. So have a heap, and so forth. And therefore, by induction, one grain of sand is a heap. And people have written a lot about this. One possible solution is to say, well, being a heap is a vague predicate. That's not really 1 or 0. It could be somewhere in between. So if you have, like a little thing like this of sand, it's like maybe 0.05 of a heap. And reasoning with truth values that are between, I guess I could just find like this, strictly between 0 and 1 allows you to reason about predicates like, well, being a heap, like being tall, things like that are not really strictly true or false. Now, if you're going to do this, you have to somehow model Booleans. What does conjunction mean? So there's more than one possible interpretation of what it means to have the conjunction of two things that are between 0 and 1. So if you take the product of them, it gives you something that makes sense. You take their max. Oh, min, that should be a min. Max is not good. That takes something that makes sense, and there's a little bit of an engineering problem there. So one of the possible ways to set this up is called Gödel logic. And this one is nice because if you're interested in constructive mathematics, intuitionistic logic, this also could be classified as an intermediate logic or as fuzzy logic, and it has two different viewpoints. And if you take propositions with value, for example, 1/2, you can see that excluded middle fails, so P will not be true. Not P will also not be true, that because it would require, in this particular logic, if P has any positive value, then not P will have 0 value. Now, this came about in as the name says, it was invented by Gödel. So what he was interested in at the time was intuitionistic logic. It was not clear if it required infinitely many possible truth values. And so the truth values in Gödel logic are easy to see because they're just chains. So if I have two different propositions, one will be either more true or less true than the other. And it turns into this axiom. So that was given by Dummett in the 50s. It's also called Gödel-Dummett logic many times. Now the specific results that we're going to talk about, if you look at first order Gödel logic, so it was shown in the 90s that this was not axiomatizable, And if you look at the proof a little more carefully, you can see that it's actually arithmetically hard. So the last thing was probably not very precise because I'm not so familiar with this proof, so I'm not sure if it gives you the stronger result. But we're going to see how this works, and this could be strengthened a little bit more without much work. Now, because we're subclassical, you have to work in a language that includes everything as primitives. And there is a little bit of interdefinability, but you're not going to get that thing that you get in classical logic where everything could be defined by conjunction and negation or something like that. And the difference between this and classical logic, so in classical logic, models are a domain, and to every predicate and every tuple of elements for the domain, you say, well, it's either true or false. Here, you're going to assign values between 0 and 1. Some basic rules of false and is false. That's pretty standard. As mentioned, conjunction will turn into a minimum. No, that one's correct. Disjunction into a maximum. Implication is a bit funny. So what's the idea here? If psi is more true than phi, then the implication is just true. That's what implication means, right? Otherwise, it's only as true as a consequent. And these, we're working on real numbers, so we have operations such as not just max and min, we have suprema. So exists will be a supremum, for all will be an infimum. So, I mean, the only thing I could say about this is that it's a very reasonable way to set up a logic with intermediate truth values. It's not the only way, there's other ways that have nice properties. But since I come from more of the, well, let's say I'm closer to intuitionism than to fuzzy logic, this is the way that is most natural to me personally.
Could you consider other quantifiers?
Yes.
Does someone do that?
So I'm sure the answer is yes, but I also don't personally have not looked at it, so I couldn't say anything very insightful. But I'm fairly sure that yes, people have considered other fuzzy quantifiers. Yeah, because when you're here, sorry, there's two ways to interpret the question. One is, there are other ways to read exist and for all. If that is the question, yes.
Well,
if
no,
you could
I mean, other. This is a function, right?
Right.
Taking the soup of all the possible values.
Right.
Right. So you're looking at all the possible values when you take the soup. You could take the average.
Right.
And so maybe that gets you something different.
So,
or some other function.
So there's other. Let's start with these. There's the. I never know how. Yes. Thank you for thank you for not making me try to pronounce that, because I never know how to do the L. So that one has these have more arithmetical flavor, like
those are like Boolean combinations.
Yes, but so there's other fuzzy. Forget about this. There's other fuzzy logics where this could be a product. This could be some sort of chopped off addition, and then they match well with things that have some infinitary version of addition and so forth. So there are many ways to set up these logics. There's literature on how to classify them and what kind of functions lead to nice fuzzy logics. So in that sense, yes, there's many other quantifiers. In the sense that if you consider one single logical system that has more quantifiers, interacting, that's like you say, like the average. Then my answer is I'm certain that it has been studied, but it's not something I've looked at, so not so familiar. Yes?
Is there negation?
Yes, I didn't mention it, but it implies falsum.
So would that always be 1 or 0?
Yes.
Okay.
So this negation will always take 1, 0 values. Again, if I look at a different fuzzy logic, I might get a different. So you could take a negation to be 1 minus a value.
I was wondering. Okay.
Yeah, but then that's a different logic. So Gödel logic, again, is a very specific fuzzy logic. There's many of them. There's many choices you can make. This one is natural if you come from intuitionistic logic and you want something that behaves similarly. Now, I said that we're working in interval 0, 1. What you really want from the interval 0, 1 is for all these operations to be defined. And all of these are, any linear order will do because you're comparing two things. But these require some sort of completeness properties, which the interval 0, 1 has, but that's not the only thing that has these closure properties. If you take any closed set that's a subset of 0, 1, then you have the property that if you have a subset of T, the infimum is in T, and then you could work on Gödel logic there. So for such a closed set, I'll have a logic GT, which is defined the exact same way, except everything is always chosen to be in T. And this very famous one is G downer, is the one that I talked about at the beginning that Hajek and other people studied. I take a descending chain going to 0 and 0 because of closure, but basically I have an upside down copy of the natural numbers living there in my truth values. And once you have a notion of semantics, you can ask about the validity and the satisfiability problems. So in this case, we set up validity as, is phi always completely true? So something is valid if it's always give me value 1. Something is satisfiable if I could manage to get it to have a non-zero value. So these are not entirely dual. You cannot say, oh, I could solve satisfiability if I could solve validity by just checking the validity of the negation. That doesn't really work here. And you will see that later, and the results show this. However, there is another way to set up satisfiability, because you might read this and say, wait, why didn't we just go ahead and say, let's make it 1? But that does also give different problems in principle, but not for this.
Sorry, if you go back to the slide.
Yes.
Are these decision problems, or do you want them? What do you want? What do you want?
These are decision problems.
So you expect some kind of decision, yes or no, if it's decidable or not. I mean, is it valid or not?
So this is mainly talk about complexity. So the results are how hard is the decision problem.
And now you can replace 1 with, say, 1/3 too, right? I mean, so you expect to have the same answer?
It'll depend on T. So I think the next slide will give an answer to that. We're working specifically with a certain kind of truth values, which, did I define it, Tyrion? All right, I put it in the slides. I didn't say this. So this subcase is about Noetherian Gödel logics. We don't have any strict ascending chains.
Well, that's why I picked 1/3.
So Noetherian is not just.
Oh, because it was here. Okay. Yeah. So in this particular case, yes, the answer is yes. Yes. In very general cases, the answer might be yes or no. But with this Noetherian restriction, the answer is yes.
But you could say less than 1/3, then that should be okay too.
So to say non-zero,
we're gonna talk afterwards anyway, so you keep on going.
Yeah, so I know that to say non-zero and to say 1 is equivalent. If you change it a little bit, I have to think a little bit. Normally probably yes, in the Noetherian case. And why is that? Suppose I have a model where b is greater than 0. So this discussion should work for b equals 1/3. So we make a new model. What I'm doing is that everything that's v or better just becomes completely true. Right? So things that have lower truth value, they retain their old truth value. But v is like, what do you call these? When you're grading exams and you say that everybody that has a 7 has a
scaling.
Yes, it's not exactly scaling, because I'm saying if you have a 9, then you have a 10, right? So
it's scaling.
So right, something like that. So the claim is that if in my old model I had the value v for phi and I upgraded v to 1, then in the new model, which should have been an n here, I get that phi is completely true. And if you try to do the inductive argument, things will work out mostly. The case where you use the Noetherian condition is the exists, because what happens here? Suppose that this has value b. B is a problematic value because it's the one where you have a discontinuity. So then, because this is Noetherian, so this will tell you that you have a sequence of values for x such that the truth value of phi of a converges to b, but b belongs to this Noetherian set, so a converging sequence eventually stabilizes. So I have the actual value of phi of a to be v, and that gets upgraded to 1. Right, so this is the one step where you're going to use the fact that our truth values are Noetherian, and you can in fact upgrade to 1. So in this special case, the answer is mostly yes. If you drop the Noetherian condition, you might get strange things. Okay, great. So the question again is, how hard is this problem? And this is going to be a useful abbreviation. This basically means phi is less true than psi. It's defined like that. What you need to know from this is that for this to be 1, I need one of these two properties. So if this is 1, then an implication is always at least as true as a consequence. So this is 1, it forces the whole thing to be 1, that's fine. What happens here? All right. So suppose that this value is not 1, then for this implication to be true, I need that for this value to be smaller than this. Okay, but then what does this mean? This is either 1, which again, by assumption should not be the case, or phi. Phi only when phi is strictly smaller than psi. So the only other way, if this is not true, to get a value of 1 is to have this be smaller. So we can talk in a certain way about the ordering of truth values using propositional logic. Okay, so how hard is this? This is very hard. So satisfiability and validity are both, well, the Hadjic result is that they're arithmetically complete. We're going to get something better or worse, depending on your point of view. So we're in first order arithmetic. We're going to add this new predicate. N is going to be a control predicate. And this arith formula I'm going to use it to code arithmetic. So it tells me everything that's arithmetical is crisp. So I take addition. I'm not working with function symbols, so you could do the relational version. And I say, well, equality is crisp, less than is crisp, meaning that it's either two things are equal or they're not equal, nothing in between. You have some basic arithmetic, just defining axioms for addition, multiplication. This is needed because equality is not considered a logical symbol the way we're setting things up. Now, what does this tell me? Okay, so as I go up the natural numbers, from the previous slide, you saw that, well, the truth values will be decreasing unless they're 1. So I need to force them to not always be 1. And how do you do this? This tells me that they're not going to be always true. It's not true that every x satisfies the n predicate. So at some point I must have something that has at least a non-1 value, something between 0 and 1. It cannot be 0 because of this guy here. So this forces me to always have positive, but intermediate values. So what are the claims?
Sorry, when you say Robinson arithmetic holds, what do you mean?
You write on Robinson the axioms, and your formula, this is a formula, is just a conjunction of this. So we're working in first order logic, so you have all the predicates of all the ariths you need available. So we borrow one and we use it to denote equality. We borrow one.
So this whole, when you get done, this whole domain will satisfy Robinson arithmetic.
Yes, well, you need to combine these two, right? Because if you're working in subclassical logics and you just put the axioms of Robinson arithmetic, you might get something a bit strange. But because we're forcing everything to be crisp, then yes, you will get Robinson arithmetic to be true. But in principle, up to here, you could have non-standard models, right? So what we're doing is controlling the standardness of the model by this new.
So n is supposed to be what?
It's a control.
Wait, how should I interpret it? Or you'll tell us interpretation.
I was going to say
I'm asking the wrong question, but
no, I was going to say the properties, but if you want an interpretation for it, it's you could think of it in a finitist way, where you say, well, 0 is absolutely a natural number.
Yeah.
So n of 0 is 1. 1 is pretty sure, so let's make that also 1.
Okay, okay.
But eventually we start to get tired and say,
Okay.
maybe 2 to the 1,000 is 1/2, and yeah.
So something n of a large number, we're not so sure.
Yeah, exactly. So, and that's what this slide will tell. So, first of all, I am forcing something to have value not 1. Maybe I get tired at 1,000, 1,000,000, I don't know, but at some point I'll have a value smaller than 1, and from then on they're going to be decreasing.
Okay.
Now, the claim is, remember my truth values are a decreasing omega chain. So the claim is that I'm forcing this to be a standard model. Now, starting from A, I have decreasing truth values, and I have 1/2, 1/3, I could skip a 4th, but no matter what I do, I have this single chain that has order type omega. So there's no non-standard part at the end of my model. But what happens below A? I could have something non-standard below A. Well, because we have addition, if I have a non-standard part at the beginning, I could translate it to the end. I'm just adding A. So a model like this will not have any decreasing sequences, so I have a standard model of arithmetic. And therefore, if I take in the arithmetical formula, so when I check it, if it's satisfiable, I try to satisfy this. If I try to check if it's valid, then I check if this is valid whenever my structure satisfies the arithmetic action, which not only forces me to have Robinson arithmetic, but also the standard values forced by the valuation of n. Then phi is true, that is just equivalent to truth of phi in the standard model. Yep.
Is there maybe then a typo in the first lemma? Should that be arith smaller than 1, or?
No, it's 1.
All right.
Yeah.
And then the
Because it's set up so that, so for example, not for all is what forces the value of A to be small. Yeah, so it should be true. So that's basically Hadrick's argument. And just by...
So
yeah,
this seems to be saying that basically the complexity of the formula doesn't change in this model. I mean, they're already complex in arithmetic, really, already to make this, whether it's valid. It's just as hard now here too, right? In some sense.
let's see.
When you say both are arithmetically
So-
hard, this formula is already in Robinson. It could be a very hard array, right? And so there can't be any less complex here.
But there's a difference between provability and validity, right? So provability in PA is sigma 1. So it is undecidable, but there's layers. So it's only sigma 1. If it's provable, you have a way to show that it's provable. If it's not, then that's where you get lost, like the halting problem. Arithmetically hard means that not only do I have no way of showing that phi is true, but I also have no way of showing that it's false. So we're already in a, so to say that something is provable in piano arithmetic or Robinson arithmetic or whatever is going to be much easier than to check that it's actually true of the natural numbers. So this embedding, because it's forcing me to have standard natural numbers, is giving me truth of phi, not probability of phi. So Robinson arithmetic is not important. I could have started with a stronger
What do
theory.
you mean by arithmetically hard? I guess it's provable and its negation. It and its negation are not provable.
Well, let's go. It means that it is at least as hard as checking truth in arithmetic. but the result, so this could be sharpened a little bit, and then I'll give the formal result, and I think that'll be clearer. So if you just stare at this a little bit, you say, well, I'm only using a very small part of what I have available in my Gödel first order logic. Let's add an extra predicate in there, just call it X. And now, if I manage to satisfy this, I basically verified the truth that there exists a set of natural numbers satisfying phi. So that gives me sigma 1, hardness. And similarly, if this is valid, then every X has to satisfy phi. So the theorem is that these are actually sigma 1 and pi 1 complete. So that's the final version of this result.
Well, with this set theoretic predicate, you have X, capital X.
Right. So the Hajduk result would be something like, if you have a way of solving these problems, then you have a way of, if I give you a formula for arithmetic, you tell me if it's true or not in the standard model. So this is just scratching the surface of Noetherian logics, because this is a very specific Noetherian truth set. Let's see what else could happen. So I'm working in subsets of 0, 1. I'm assuming they're Noetherian. If I turn them upside down, they're well-founded. So if I turn them upside down, they look like an ordinal, but there's a rule that 0 and 1 are truth values. So they turn into successor ordinals. So if I take a Noetherian set of truth values, turn it upside down, I remove the top element, I get some ordinal alpha. It's countable by standard second countability arguments in the reals. And moreover, it's not hard to check that for Gödel logic. If I transform my truth values by an order isomorphism, I will get the same validities, the same satisfiable formulas. So I could forget about T and just think about the ordinal alpha. So the logic that has this order type is G alpha down arrow. And the question, so these are what we call Noetherian Gödel logics. And the question is, how hard is satisfiability and validity? Now, the trick is going to be the same trick as before, but now let's try to code set theory. And actually, I'm very thankful that in the previous talk, truth in L alpha was already discussed, so that'll help me a little bit. So now we're passing to the language of set theory. And just quick reminder, if you're in the ordinals, you could do a little bit of arithmetic. You certainly could have addition. And the what we call principal numbers, the kind of meaty ordinals, are close in their addition, right? So these are additively decomposable, means that I could write it as a sum, and if I can't, it's indecomposable. And what is a definable ordinal? Well, it means it has some definition. Specifically, I'm going to think about sigma 1 definitions. And to define an ordinal means, well, I have something that happens at that ordinal, and it could happen again later, but I want it to not happen below. So a sigma 1 definable ordinal is one that's the first ordinal satisfying some sigma 1 property.
So,
Yeah?
you mean, so sigma 1, you just sigma 1 in the language of set theory, or sigma 1
Yes, so,
in the language of arithmetic?
yeah, I went a little fast through this. Gödel set theory, so you have set theory, but you have classes. And
Okay.
I'm not working in the theory, I'm working in the language. So the language is this: I have epsilon, I have classes, I have quantifiers over elements and over classes. This constant will be useful later, but that's not so important. And sigma 1 means I have an existential quantifier over a class, and then something inside that has all the quantifiers I want over elements, but no more classes. Okay, so now this sigma 1 alpha, the notation is ours. I hope I'm not messing up some recursion theoretic notion that we set this up for convenience. So by sigma 1, 1 alpha, I mean sigma 1, 1 and L alpha. So there should be they're subsets. They're subsets of natural numbers that are defined by some property that happens in L alpha, and that property should be a sigma 1, 1 property. There's this is a small variation. It'll come out later because we need it for some of the results. This just means, okay, I'm not going to quantify over subsets of L alpha, but things that are below alpha. So these are definitions, and we're going to use these to say what the complexity is of the validity problem of G down R alpha. And first, let's start with the nice alphas. So the nice alpha are the ones that are sigma 1, 1 definable and also additively indecomposable. I have no idea how much time I've been using. Let's see. And in this case, we get something that looks very similar to the original theorem for G down R, which says that satisfiability is sigma 1, 1, but now of alpha, and validity is pi 1, 1, but now of alpha. And what we're going to do is a lot like we did before, but now we want to force a standard model, not of the natural numbers, but of L alpha. And in this part, it would be nice to make some drawings, which I can't do right now, but basically our truth values look like alpha going upside down to 0. And by something similar to what we did before, we're going to say, well, the ordinals have decreasing truth values and they go down to 0 along alpha. And but that doesn't force my ordinals to already have a order type alpha, because, for example, well, alpha has to be countable, and any countable limit ordinal is an omega limit. So my model could think that alpha is just omega, even though I have all these unused truth values in the middle. And that's why I want this ordinal to be definable, to make sure that I use all the intermediate stuff. So we start with, before we were doing a Robinson arithmetic, the trace is actually not so important, but what we wanted to do was find something that's finitely axiomatizable and gives me enough structure so that everything else works once I ensure that I had my natural numbers. What we're going to do here is same idea. We want to get enough set theory going to make everything work out, but we want to make sure that it's finally axiomatizable. So I can't just set FC for this purpose, but Kripke-Platek set theory is good enough for what we're doing. So some weakening. So first of all, we remove the power set axiom. We restrict foundation to pi 1 classes. So foundation as a scheme requires arbitrary quantifier complexity, but if I write it like this, you could turn it into a single formula. Same idea, separation is now restricted, replacement restricted, so all of this becomes single formulas. And again, I need, because I'm working in a subclassical logic, I need to control that things are crisp and equality is transitive and all this stuff. And what I was saying, that we're working with this specific set theory because it's strong enough to do what we want, but it's also finitely axiomatizable. And I'll also use KP for the axiom itself. Okay, so how do we force our standard models of L alpha? And you see this N guy coming back. And so now you have this new thing that KP holds. This constant O is an ordinal. We'll use that to force us to have a chain of length alpha. And this part here is exactly what we did before. So what this says is that the elements of O, so O is an ordinal, they're linearly ordered. And as I go along that linear order, remember that this forces me to have decreasing truth values. So I might have truth value of 1, but at some point they start to just fall to 0. If I think of everything upside down, the truth values are converging to alpha. And okay, so that doesn't necessarily give me an alpha chain because it could be a bit shorter than alpha and just going very quickly. But let's make sure that doesn't happen, and that's where we use this. So we have our definable ordinal, definable by some formula that exists as set y, such that this property here holds, and here you don't want any second order quantifiers. And now I take my psi, which said Kripke-Platek holds and n is decreasing and so forth, and I add this, that if I look at the constructible hierarchy up to O, with some predicate y, this satisfies this formula, right? So anything that satisfies that particular formula, the O part of it, well, the y will witness that the O part is isomorphic to alpha because alpha is defined by this sigma 1, 1 formula. That's what I just said. All right, so now, satisfiability. This is what we did before. We satisfy these premises that force the standardness of the model. We ask for phi x to hold. So that's equivalent to the sigma 1, 1 formula happening. Now you will notice something different happening in validity. I'm adding this n of 1. Why am I adding that? What is the effect of that? So if this is valid, that means that any model satisfying this assumption will satisfy these two things. But if I only pay attention to the ones where n of 1 is not 1, then I'm forcing all of my ordinals except for 0 to have a non-1 value. And then it's an even more extreme version of this finitism where you say, well, I accept n to completely be 0 to completely be an ordinal, but everything else is only partially so. And the fact that I could do this here for validity, but that trick will, if you try to adjust this trick so that somehow this will only be satisfied if n of 1 or 2 or whatever is not precisely 1, you will see that it doesn't really quite work for satisfiability. And this will give us some difference in the results, getting back to my point at the beginning that these are not exactly dual problems. All right, so what is the, wait. So what is the general case? So in this case where the ordinal is nice, the standard case, by a standard case I mean that alpha is definable and it is additively indecomposable, then I get these two results which actually are dual to each other. Sigma 1, 1 alpha is dual to pi 1, 1 alpha. In the general cases where things will get kind of funny. So let's see. So this general case for satisfiability, I'm being very exhaustive. So what does this mean? That's classical logic. And we know this is true because of Gödel's completeness here. So yeah. This is a theorem I talked about more at the beginning. Sorry, so this restricted to omega is a theorem I talked about way at the beginning, which is sigma 1, 1 complete. And in general, when my ordinal is also definable and additively indecomposable, then I get this analogous result. Now the bad cases. What if it's additively decomposable? Okay, so this one's funny. This beta could be huge. It could be, omega 1 ck plus little omega, and then this tiny thing wins, and the whole complexity collapses to just omega. Which I think is a bit surprising, but that's the way it works. I'll get back to that one. And finally, I won't talk that much about this case. Well, I'll talk about it in the validity part. If I have something that's not definable, then I'll only get this weaker version. So remember, this means that I can't really look at L alpha, but I could look at the L betas that are below L alpha. But why does this happen? So this, again, remember this trick where I force all of the ordinals that are not zero to have non-one truth values. It's not going to work for satisfiability. You could try it, it will not work. And what's going to happen is that I'm going to lose initial segments are just going to be, I'm just going to lose all the information about them. And why is that? So remember that we said that if I take any truth value, I could collapse it to 1, say everything that's this true is completely true, and only keep the stuff that's underneath. So in this case, if I have that alpha is beta plus 1, I say, well, everything that's beta or below, I collapse it to 1, and I only keep the gamma part. So then we get a T gamma model that, so from a beta plus gamma model, I do this trick, and now I get a T gamma model because all of the beta part has completely disappeared. And the converse is actually just generally true. So if I have any model based on a smaller truth set, then I just view it as a model on the original truth set, and the other truth values are just unused. Okay, so yeah, in additively decomposable cases, only the tail matters. Everything at the beginning, doesn't matter how big the ordinal is, it only matters the very last part in its counter-normal form. So what happens for validity? Let's see. Now, we start with a countable ordinal again. So this is a theorem. When alpha is exactly 1, again, we have classical logic, and again, Gödel's completeness theorem tells us that something is true or valid if and only if it's provable, and that's a sigma 0,1 thing. This could be extended to any finite number of true values in a similar way. This we already discussed, and again, I want to stress the difference from the satisfiability case. I don't care about decomposability here because, again, I could force all of the ordinals to have non-one truth value. And again, we have the problem with the non-definable ones. And now I'm going to get into a little more detail about this one. Suppose I have something that's not a sigma 1,1 definable. So the claim here is that to check that something is valid in G alpha, I just have to check that it's valid in all the smaller betas. And the reason for this is very simple. If that weren't true, if I had that phi is valid everywhere below alpha, but suddenly not valid at alpha, then not phi gives me a definition for alpha. So that cannot be the case. So checking validity at G alpha is going to be equivalent to just checking validity below alpha. There's actually a little bit more work here to be done. There's I'm skipping a not too trivial part, but I think from this observation you could believe that this is at least possible. All right. So what did we do? So these classical results in G down arrow, they generalize a lot when you start to look at other Noetherian Gödel logics. I would say that this is okay. So in the case that we have definable in the composable ordinals, these results just generalize in a very straightforward way. But even when we don't have these nice cases, we completely can classify the complexity of all of these logics. I think that was a very surprising part of the results, that things just work out sometimes a little more complicated than others, but we know exactly what all of these complexities are. Now, there's the opposite types of logics. So we're considering truth values that are decreasing to 0. but you can also consider truth values that are increasing to 1. And just as in the Noetherian case, this has been studied when the order type of this is omega. And you could do a little bit of coding there and also get, but now you get a lot less complexity. So it's still undecidable, it's still worse than classical logic, but now you just get pi 0 to completeness for the validity problem. And of course, this very naturally raises the question, so what happens with other order types? We are starting to think about this, we don't know. But this could lead to something very interesting, which is, well, we know how many Gödel logics there are, but can we describe exactly what they look like? So something is known that to know what a Gödel logic looks like, you have to know the limit behavior at 1 and the limit behavior at 0. Things in the middle can more or less get forgotten. If your truth value set is perfect, you get a specific logic. Some things like this are known, but can we get a complete classification? So let's think just about 0. So you have the case where 0 is perfect. So there's a perfect set that approaches 0. So that's been studied. We consider the case where you have a sequence converging to 0, but with no increasing sequences. You could imagine all sorts of intermediate cases. You could imagine a bunch of increasing sequences that themselves descend to 0. How bad could this be? How many different cases are there? Is there enough of a collapse for us to classify and say you have either this type or this type or this type? We don't know, but I don't think it's hopeless. I think it's worth giving this problem at least a shot. Now, to get a little bit to the topic of the conference, should we do reverse mathematics on these kinds of logics? And there's something. So as a purely mathematical exercise, of course, it could be interesting and you could have nice results. But there's something that I think is a bit funny about these. So from pure classical logic with our descending sequence of truth values, we already got arithmetic. So you don't actually need any arithmetical axioms to interpret arithmetic as long as you agree that your truth values are going to be this decreasing sequence. So this gives you a perspective where arithmetic is baked into the basic logic, and classical logic itself is sufficient. Well, sorry, classical. First order logic itself is sufficient to do arithmetic without explicitly adding axioms. So there might be something to say about reverse mathematics in this setting. It's probably something very similar to doing reverse mathematics on top of omega models. I don't know, I think it's something might come out of it. Anyway, that's all I wanted to say, so thank you for your attention.
Okay, thank you very much for the talk. Is there any question? Maybe, oh, so maybe on the chat. Okay,
So
yeah.
maybe just the last question can be interpreted in two different ways. Either you do
Okay.
reverse mathematics using Gödel's logic in place of classical logic. This is maybe what you intended.
That's what I meant, yes?
Or otherwise, you could just, I mean, you are proving theorems, right? Which could be analyzed using reverse mathematics, what kind of axioms
Okay.
you need to prove, I guess. I mean, just in the context of classical reverse mathematics, let's say.
So the reverse mathematics of these theorems.
Yes.
But didn't, who said this? I think Simpson,
Well, maybe
was that
yeah.
reverse mathematics should be about core mathematics and we shouldn't do it with logic.
I mean, there is reverse mathematics of a classical completeness theorems for
Yeah, I
classical
was-
logic
I was,
and things like that. So
It was not meant to be taken too
It's just a
seriously.
comment, I mean.
Yes. So the main thing you need is the notion that these ordinals are there, but aside from that, the rest of the proof was fairly elementary. So yeah, it's worth looking at. I don't think it'll be terrible. The worst thing that could happen is if you're in a weak system, then you don't have that many ordinals to feed into this theorem, but I don't think it'll be too bad. But yeah, so it could be done.
Any other question? So let's thank the speaker again.